Great. Okay, that's it. We're live. So welcome everybody. Thank you for coming along. And I think everybody knows the subject of today's rendezvous. And Alex has done a phenomenal job, I think, preparing an interactive session for us. And I'm not going to spoil that by trying to give an intro. I'll just hand it over to Alex to guide us through the next hour and a half.
All right, thank you, Steve. So welcome everyone to another Subsurface Rendezvous. I'm very honored to be here together with you to talk a little bit about something I'm very passionate about, geothermal energy. I just wanted to show my face and say hello before turning off my video, just to make sure that everybody can hear my voice correctly and there's no issues. I will switch to the actual presentation. There we go. Turn off the video. So, Pareto view of geothermal energy proliferation. This is meant as a community exercise where I wanted to bring together people like Matt and Robert from Agile and other people from the oil and gas industry who are interested in branching out to geothermal energy, together with people who actually work in geothermal energy and see what it is that together we might be able to do. On top of this, what I'm really interested in is trying to figure out what it is that we can do to improve the proliferation of geothermal energy, make geothermal energy projects successful, or on the other hand, stop the failure of geothermal projects. And so there are two logos on here, which is Software Underground, which is a beautiful community of people who help out with coding and softwares and ideas when it comes to earth science problems, and Stand Up for Energy, who are the people who pay my bills at the moment. So, as you might have seen, there are 3 links either at the bottom of this YouTube video or inside of the Slack channel that you can see here. One of them is a PDF with instructions. Another one is a list of questions. I made 50, but I'm not expecting everybody to fill out all 50 or even be capable of answering all 50, because geothermal energy is too big. I wouldn't be able to answer all of them myself. And together, I would like to create a reference list of things that are promising or are issues that could hold geothermal energy back. I have made a big start. There's a lot of things that I have that are still missing there. And if there's things that I don't know about and you do, I would love for you to add to this list. If you are just here for a little bit of entertainment, good on you. You're very welcome to be here. We're going to be working with Slido, and we hope that this will stay open for longer, but the Slido questions might close on the 1st of April. I'm not sure about that. So what we will be doing for the next hour, 1.5 hours or so, is I'm going to be talking for a little bit of an introduction for people who might not know too much about geothermal energy. Talking about why geothermal energy matters, and then describing some exciting developments that might make geothermal energy explode. It might help geothermal energy become that much more successful. Then I'm going to be talking about some issues that geothermal energy has come up against so far and might continue to come up against, where we need solutions. And the title says Pareto view, so I need to explain what that means. Then we'll be doing the community exercise. We can play a game of Ask Alex if you have any interesting things that you would like to know about geothermal energy. Just shout it out and I will try my very best to give you answers where I can. And if we have time left, we could have a little bit of a community discussion. So let's begin with why geothermal energy matters. As you may all have heard, the world is going through an energy transition, and most people talk about climate change, how CO2 is affecting our climate, and what effects those will have in the next 50 to 100 years. What tends not to be discussed so much is that there are other reasons, more pressing reasons right now, that we should phase out fossil fuels and go for renewables instead. One of these is air pollution, which a new publication has come out recently, has shown leads to millions of deaths each year due to particles in the air. Excess deaths, similar to how smoking leads to excess deaths. A very interesting thing that has happened recently is that renewables, mainly solar cells and wind turbines, have become cheaper than fossil fuels like coal. But that doesn't mean that we'll be able to just change. It's a very important step, but fossil fuels are here to stay until we make the transition, until all the infrastructure is ready for us. And so when we look at the global energy consumption, we mainly use energy for electricity, transport, and heat. And very interestingly, heat is a little bit more than 50% of the total amount of energy that we use, more than the electricity and transportation combined. Now, this chart here shows that most of the heat is currently being produced by fossil fuels. And when we look at something like geothermal energy translates to using the Earth's heat. So if we're consuming heat, we can just use the heat directly, or we can convert it to electricity. So geothermal energy does both electricity and heat, where the top 10 kilometers of the Earth have enough energy stored for the global energy consumption for the next, citation here says 217 million years, if you take away the exponential increase of consumption, of course. But that is the amount that is currently stored in the top 10 kilometers. That, because the Earth is more than 1,000 degrees Celsius in most of its volume, that is renewed every year. So geothermal energy is a massively abundant resource that we could use to phase out this part, which of course is easier said than done. One thing here that I think is very important is that geothermal energy is not something that you can transport like oil and gas. It is something that is available locally. So if you have, for example, the East African rift system, there the energy that would be created from the rift would be available for the people there directly. So the beautiful thing about geothermal energy projects is that they usually include multiple other synergies, which means that when you have energy coming out of the production well, this can be multiple, like 250 degrees, like 110, I think 97 degrees is organic Rankine, level possibility right now, which you could use for electricity generation. That costs a certain amount of temperature. So in goes one temperature and out comes a lower temperature. But that fluid would still be hot enough to be used in a different societal application, like pasteurization, for example. When you use a little bit of energy there, a lower temperature comes out, which is still hot enough for something else. So this is what they call cascade heat usage. There are many different geothermal projects that are specific for one thing. For example, if you create a tunnel, then the water that would flow in the tunnel naturally needs to be pumped out. This can be used directly as a geothermal heat source, and that might just be like the quality of that might only be this much, so you would use it for fish farming. But if you have higher temperatures, you could create a cascade. And at the same time, if you were to use a Carnot machine, like the reverse of a fridge, you would be able to increase the temperature of that water for the cost of a certain amount of electricity. And these heat pumps can nowadays have a return of 6 values of heat for 1 value of electricity in industrial uses. Then you can go further with this idea by using a different energy source to superheat the geothermal waters. If you were to use biomass to heat water from a river, for example, you would need a certain amount of biomass to create electricity. But if you use hot water from a geothermal resource and then heat that up to the same temperature, you would need less biomass. On the other hand, because the thermodynamics improves for electricity generation, you could create higher temperatures using the same amount of biomass, and with that create more electricity, have a power increase. Here is another example where there's a thermal solar being combined with geothermal brines. So heating up geothermal fluids with another resource allows you to have more heat or to have more electricity, a combination that would allow other renewables to proliferate as well. And then there's mineral extraction. About 10% of the global lithium consumption, which is used for batteries, for example, runs through geothermal power plants that are in production right now. If we were to increase the amount of geothermal power plants we have, then more of the required lithium would be available for us to extract from the subsurface without us needing to make big holes in the ground to mine it. One issue that needs to be taken care of beforehand is the exsolution of silica, which scales or clogs up the pipes of a geothermal project. And luckily, silica is something that is required for different applications. So if you can get different grades of silica, you can sell them for different prices. And lastly, depending on your subsurface, you will also be able to get rare earth elements, which are used in electronics. Short sip. Right. One very interesting solution for climate change, additionally, is CO2 storage, where the Carpfix project that has been running since 2014 in Iceland, Nesjavalir, has been injecting 66,000 metric tons of CO2 since 2014. At the same time, you can combine a geothermal power plant with a CO2 storage facility by using CO2 as the fluid that you pump down and extract back up. The beautiful thing about this is that as CO2 goes deeper, it gets denser, pushing the CO2 into the reservoir, and as CO2 heats up, it expands a lot, pushing the CO2 out of the production line. So this is called a thermal siphon, which allows you to save on pumping energy, which is a parasitic power. And one of my favorites is energy storage. So when we think of energy storage, there's batteries and there's pump storage, big hydro dams. There's also chemical storage where you can put methane or hydrogen into the subsurface, pump it back out again. Or something called compressed air energy storage, which is very efficient. Now, with the idea of compressed air energy storage, you can create a geothermal battery which produces more electricity than you put in. And I don't have enough time. This example could be the entire talk today, but I'll try to give a short explanation. If you have the oversimplified ideal gas equation here, and you keep the volume N and R equal, and then you increase T, then you will increase pressure. So as you use the thermal energy from the subsurface, your pressure, which is how you are storing your energy, increases again. And when they tried this out in the US in a pilot project, at the beginning they got out 212% of what they put in. And after 30 years, as they estimated it, they got out 144% still. So this would be very beneficial for the proliferation of renewables that are variable. And these are, for example, solar and wind. Now, for solar, most people understand during the day you have the sun, and during the night the sun goes away, so you don't have solar energy anymore. But there's also different cycles. If you have cycles of weeks or if you have cycles of months, there's more or less energy being created over those time periods as well. And most other resources are not capable of handling these longer period cycles when it comes to this variability. Putting a very big cap on how much solar and wind can be producing at a certain time. And so there's examples of, I think it's Florida, where for certain parts of the summer, they just turn off all production because they can't do anything with it. So it's very important that we start storing this energy. That brings me to exciting developments. First one is drilling. And I will turn this on. This is something I got to play with during my bachelor's thesis. As you can see here, when you put a very hot source, either a flame from methane or a laser, what you will get is pieces of rock flying off like popcorn. It's really fun to see this in the lab. This is one example of contactless drilling. And the beauty of this is that when you have a mechanical drill, the deeper you go, the more of a problem it becomes when your drill bit wears out. So if your drill bit is no longer capable of increasing your well, you have to pull it all the way out, change the drill bit, and put it back in. So something like a contactless drilling technique would be able to save you that time already. On top of this, these advanced drilling techniques are faster in drilling by themselves without having to think of this additional step. And so it's estimated that being able to do drilling like this will reduce the cost of geothermal wells and other drilling substantially. What is also very interesting is that as we have been drilling over the years, we're getting better at it. And so this also comes back to the costs. If there's a particular geological setting that you're drilling into, and people have been drilling in the same setting for the past 10 years, they have more ideas of what can happen, what they need to do, which kind of layers they're going through. And this has made it cheaper and cheaper over the decades for wells to be drilled. Next to this, there's seismic while drilling, which basically uses the noise that the drill bit creates as your seismic source. And something that for logging is very interesting is using the time when the people who are doing the drilling are taking their break to do the logging in the well, so that everything is more streamlined. From drilling, we go to, how do I go to the next page? Go to deep drilling. So if we're talking about the top 10 kilometers having so much energy stored, there is more difficulty as we go deeper, but there's also more potential as we go deeper. And so there have been quite a few deep drilling projects to try and get deeper and learn more. There's quite a few challenges that are related to this, and the more of these challenges we learn how to work with, the better we will get at getting to the full potential of this resource. One of these examples is IDDP, and the first one in Krapla, Iceland, drilled into magma at 2 kilometers depth, which was unexpected but a really cool result. And here is an example of a paper about that. And IDDP2 drilled into a supercritical reservoir at around 4.5 kilometers depth on the Reykjanes Peninsula, also in Iceland. And IDDP3 is currently in the planning phase, where I have been working. There's some shameless self-promotion. There's here on the Reykjanes Peninsula, underneath what is called Krýsuvík, a very big body which we interpret as a supercritical reservoir, which, if this would be used for geothermal power plants, this could be used for the IceLink interconnector, which would send energy between Iceland and the UK. So if you want to know more, you can read that paper that should come out next week. When we talk about deep drilling, there's another project in Helsinki, Finland, where they've come up with a new business model. As I was saying before, if you have the same regional geology, then it becomes easier for you to do the drilling. It becomes easier for you to understand what kind of needs you have. And in Finland and in Sweden, there's the Baltic Shield. And the Baltic Shield is similar over a vast region. Most of Finland is in the Baltic Shield. And so the SE1 ESPO project is a project of about 100 million euros trying to figure out how to do an enhanced geothermal system, create permeability at around 6 kilometers depth where there was no permeability before, so that they can do it again and again and again for other projects that would be paid for by investors, and then start paying for the next one as they start producing. And this business model has been estimated to be able to create enough return on investment to have a new system, what do you say? To start having return on investment within 6 years, which, as you will see in a moment, is massive. One thing I think is really interesting is borehole stress inversion. Inverse method basically use the physics that we know and try to get back at how the subsurface behaves, what it is that created our data. And so when we have fractures, which are the largest, they have the largest permeability for our fluids to flow through. These fractures create anomalies in the stress. And these anomalies you can measure inside of the borehole itself using calipers, for example. And so by using inverse methods, you can get back to these fracture networks. And if you combine this information together with geophysics, you can start getting a better understanding of where the fluids are going, which allows you to do fluid modeling, reservoir modeling. Here we're talking about thermo-hydro-mechanical chemical modeling, which is a coupled code with a lot of different types of physics. And this is extremely complicated and very computationally expensive. If you have one reservoir, you can have 4,000 clock hours for CPUs. If you do that on a supercomputer, you can still do it within a day, but it is very expensive. On top of which, you tend to have insufficient information. So you have a deterministic result, but you cannot say that what you put in is what you should have put in. So you tend to need to take statistical distributions and do something like a Monte Carlo. And so something that I did for my master's thesis, and we published our first paper on, is creating a cheaper model that makes simplifying assumptions so we can calculate this much, much faster, and then look at the error between the true result from an expensive supercomputer code and this one to adjust the information that you get out. At the same time as we were doing this, there was the Los Alamos group who did a very similar thing using different methods. And they did multi-fidelity Monte Carlo, which for what it is that they were trying to do, we're able to get 10,000 lower quality runs for the price of one higher quality run, and then be able to adjust the lower quality information to the higher quality information to get a very robust result in the amount of computational cost that they had available. Which brings me to distributed acoustic sensing. One of the things that makes it harder to do the modeling, as I said, is not having enough information. And having a lot of information is what distributed acoustic sensing creates. It uses a fiber optic cable and sends a laser back and forth. And as there are irregularities in the fiber optic cable, the laser gets sent back, which an interpreter can read. So theoretically, you could have a measurement every 10 centimeters if you want, but this particular paper did it every 2 meters for a total of 13 kilometers. And so for this one earthquake that they have here, you have a lot of information coming in. And this fiber optic cable, when it was laid down, created 12 gigabytes of data per week for earthquakes and more. When it comes to distributed acoustic sensing, you can use them for seismic waves, as we've seen here, but also deformation. So if you were to put an optical cable inside of a borehole, and then there's something deforming the borehole, then you will be able to see exactly at which particular centimeter of your fiber optic cable that deformation is happening. And another possibility is to see heat in that sense. And then we have modular energy conversion. One of the problems that geothermal energy tends to have is that all of the costs are upfront. You have to pay for everything before you have anything to show for it. And then when you start producing, all of that needs to be paid back. And having a very big power plant with a very big turbine is very expensive. So if you can pay for a smaller energy conversion unit, you can already start producing from the very first well. Instead of needing 33 successful wells for a very big turbine, you can start using the very first well, pay a little bit for a small unit, and then start adding units as you are increasing the amount of wells. This means that you can have an earlier return on investment, and they don't have to be custom built for the project that you have, which also means that they can be cheaper overall. This brings us to issues. It's not all rosy. These issues are also big. One thing that Ladislaus Rybach, the professor emeritus at the ETH, discussed with us a few years ago, is that geothermal energy is invisible for everyday people. It's not like a solar panel or a wind turbine that you can just see outside, and most people just know. It's something that's below the ground. We cannot see through the ground. Most people do not know what the layers are called just 3 meters underneath their feet. So because it's underground, it becomes intuitive and it's unknown. And all of this comes together to make people less interested in it and having less political support. Then there's induced seismicity that has cost us several important projects, which include Basel, Switzerland, St. Gallen, Switzerland, Pohang, South Korea. And I did my education in Switzerland, so most of these examples are from Switzerland. There's a project in Haute-Saône at the moment looking for approval to get started. And there's still questions about if they can or not, because there's a lot of political opposition. And in this particular case, one of the issues can be using anti-geothermal sentiments as a political platform, which could also be the opposite, of course. Geothermal energy is something that you want to strengthen. One interesting conversation I had, if you look at Basel, the largest earthquake that basically cost the entire project was a magnitude 3. And when you talk to somebody from Chile who has a magnitude 6 almost every month, that's not really anything to be worried about. But if you look in Switzerland, a magnitude 3 is almost as big as the biggest one available on a yearly basis in Switzerland, so it immediately becomes. brings us to volcanic upheaval, and some of you may have been following this, especially in the Slack channel. After about 800 years of quiet, the Reykjanes Peninsula has started erupting again. And this is about 8 kilometers away from a geothermal power plant, which is built on such lava. And there's a local town. And it's about 30 kilometers away from the capital of Iceland, where 2/3 of the population live. Other examples of volcanic upheaval are lahars, which are big streams of ash that come hurtling down the mountain at you. It's not something that you want to experience. And in general, if you have a stratovolcano, your air travel can be halted as well. So one thing that is extremely interesting about this, which my second paper of this year is about, is that the amount of earthquakes that were created during the entire unrest period, which lasted for 14 months before the first eruption now, with a likely eruption still continuing for years or maybe decades to come. And if we look at the 30 years prior to this period, there were, including the entire year of unrest, there were about 40 earthquakes that were larger than magnitude 4. And then when the swarm that prepared for the eruption that is currently going on started, there were more than 50 earthquakes above magnitude 4 in just a few weeks. So this is a town right here, and people have just started to wish for the eruption to get started because they were getting sick of being woken up in the night, having an earthquake again and again and again. So this is another issue that you can have, having a geothermal power plant with the people required in a high enthalpy area, that nature will wake you up during that. And there's economics. One of the problems that geothermal projects tend to have is that it's hard to get insurance. If you have a well being drilled in an oil and gas company, you can miss 20 times, and the 20th hits the mother load, and it pays for all of the other ones. In geothermal energy, this is not something you can do. In geothermal energy, if one of your wells misses and you are not capable of using that well, then it's very likely the end of your project. Next to this, the return on investment for electricity generation from EGS has been calculated in several studies to be around 30 years. This is an example where you only take electricity generation from the EGS, none of the synergies that I discussed before being taken into account. So that's a very long time before getting your money back, and there's several risks involved that could mean you don't get your money back at all, which is why it is a big issue that needs to be overcome. As I said before, because geothermal energy is less known and it's in the subsurface, there's smaller governmental subsidies in comparison to wind and solar. All right. So that was my description of geothermal energy. And now I'm going to go through several ideas in the past that have been extremely influential. The Pareto distribution is commonly known as the 80-20 rule, which I think is the wrong way of looking at it. But the 80-20 rule says that 80% of your success comes from 20% of the things that you do. And 20% of the things that you do take 80% of the time. That's one example of looking at it. But when we look at ideas, we have Shannon's master thesis that created both information theory and computer science. This, how much information content do you have in the signal? Complex numbers is something that took 300 years to be developed in mathematics. And this is something that's in most advanced technology. Most of what we do as geophysicists. And it was used in Shannon's master's thesis. So inherently complex numbers was a more important idea than Shannon's information theory, which was massive. Here, if we have natural selection, you can use this to explain most of the things that we see around us, from how scientific understanding evolves biological species, cultural phenomena, like the YouTube memes that we click on, and the technology that we're currently using for this subsurface rendezvous. Was very different 2 years ago. So, when we look at this, we can create this Pareto distribution, which is a power law. And depending on the decay constant of this power law, this will be steeper or shallower. And one thing that we would like to do is elevate the power law so that the area underneath the curve increases. So the idea is to have this community exercise, have people look at which are the things that are vital for geothermal projects, and which are the things that are most common or most likely going to lead to the failure of geothermal projects, and see if we can do something about that. So, community exercise is the positive side in the past, in the future, and the negative side in the past and in the future. We want to know which ideas, methods, and technologies have most contributed to the success of geothermal projects and the proliferation of geothermal energy in the past and future, and which issues have most hindered or led to the failure of geothermal projects in the past and are most likely to do so in the future. And as I described at the beginning, the links that were provided include a list of questions, and the first 4 questions has us rank order this particular list. This list is not necessarily complete. It's not necessarily the best way that you would subdivide them. It's one choice. It's exploration, characterization, and monitoring, because they tend to use the same technologies. There's drilling, where you could put logging and borehole casing in there as well. Reservoir stimulation, modeling the synergies with other technologies I was talking about, conversion technologies, economic models. I think data proliferation is something that is very interesting right now. Most universities now need to publish open access papers When you create something, you're asked to include your data. You're asked to include code. This is something that has been discussed in the Slack channel as well. And one thing that I think is an interesting question is leadership. Do we need an Elon Musk to gather us together and make this happen? Are there certain things that is required from leadership to lead to the success, or is this of lesser importance? So, this one person. Right. So you are welcome to start answering the questions now. And while everybody is doing that, I would open up the floor for any questions you might have.
You've used some really big categories here. And I thought it might be useful to do two things to help people answer the questions. And the, sorry, the sun's just come up here. And the first thing is maybe be a little bit more in terms of a definition of what you mean when you say geothermal, because at least, you know, like in our hemisphere, like whether you call that the European versus the everywhere else hemisphere, when we say geothermal, we mean high temperature, naturally advecting, convecting geothermal, which is quite a mature technology in contrast to a lot of the things that you're talking about in terms of like engineered systems, low temperature systems. Did you want to talk a little bit to, when we're answering this, are we talking about which kinds of technologies? Are we talking about the European sphere of engineered and hot sedimentary aquifer or lower temperature? Or are we talking about a sort of wider, you know, sort of the more mature volcanic or deep circulation natural advecting systems?
Thank you for your question or suggestion as well. For me, as I started, it's the global energy consumption. So if we're talking about a single household installing a ground source heat pump, or somebody doing a very big project next to a volcano, or trying to get into creating batteries in sedimentary rock using CO2 plume geothermal. Those are all ways of getting to that point. I don't make the distinction so much between what type of geothermal energy we are using. We're using the heat of the earth, and depending on which setting you have, you will get different problems. If you have different needs, then those needs need to be met in different ways. And so I'm rambling. Does that answer your question?
Kind of, yeah, like that you're just talking about energy consumption out of geothermal as the big category. And I guess my only specific question is, when you say modeling, what do you mean?
There it's again, I think I should take this back to the Pareto distribution.
Everything from conceptual modeling to all the computational techniques, or are you just talking about?
Mostly talking about the computational techniques, but
okay.
I do agree that the way the word is used
Yeah, so you're talking about computational modeling.
Basically.
Right.
As opposed to actually building a model.
No, so in geothermal exploration, a key tool is the development of the conceptual model, which is an integrated description of the resource that has a particular format. And it has to do with the fact that we typically run with a really low data density. So we use a lot of analog reasoning to develop resource decisions. And so you generate this integrated description, this conceptual model, and it's the conceptual model that guides your probabilistic resource assessment that becomes the framework for your computational model, your full field reservoir simulation, and your well targeting decisions. Outside of high temperature, or outside of, I guess, hot water through to high temperature, like that 100 degrees Celsius and above, like people working in engineered geothermal, it doesn't seem to be a feature so much of the discipline. But when you're working with naturally advecting or convecting systems, it's the thing that floats to the top every time that defines whether or not your project is a success.
Can I ask another question then?
Can I quickly answer one part to this, and then I'll get to you, Steve. If you look at GemPy, this is a way of combining a conceptual model into the numerics. And I have economic models here as a separate category, but you could put it inside of modeling as well. So to get back to your very first thought, when we think of geothermal, when we think about modeling, when we think about any of these subsets, there will be, for the aim of the energy transition, things that are more important and things that are less important. If we create 1 gigawatt power plant, or we have thousands and thousands and thousands of single home ground-source heat pumps, one of those will have a bigger impact. And so I think this graph, which I hope you see the graph, right?
Yeah.
This graph here is one filter through which I would like to see these problems, where the conceptual model that you're describing in high enthalpy systems could be extremely important, even in EGS systems, and people are not doing it. I don't know. Like, that's one of the things that I would love to find out. And what I really love in my own work and about geothermal energy is cross-discipline, what's it called?
Interdisciplinarity.
Can you say that again? Not interdisciplinary, but cross-discipline fertilization.
Pollination. Yeah, or
pollination.
Fertilization.
Okay.
One of those two.
Cross-pollination.
Yeah.
Yes, just taking ideas from completely different places and applying them to other fields. And because geothermal energy has so many fields associated with it, it becomes really easy to find people who are in a different discipline who can still think within the problems that you're working with, who can say like, hey, that is exactly what we do in these other things. Let's see if we can use these technologies. It's what inspired my first paper. Sorry, Steve, please.
Yeah, I just want to ask maybe a couple of questions, which is for the geothermal noob, because I don't know much about geothermal at all. But so my context is I think I get what you mean, as in you're looking at global energy usage. And because I've been reading a book called, which I found finding helpful anyway, the 100% Solution for Climate Change, which talks about this sort of thing where it's potentially not the obvious developments or projects that will yield us the biggest gains overall. So I think that's the sort of thing we're trying to look for, I thought. And just on what Irene said, I just want to clarify that when you say the engineered versus the traditional or the more mature, is it right that the more mature is because that's where you're drilling into basement rocks and that's, no, it isn't. Okay. Okay, let me rephrase the question then. Is it the engineered, is it type of geothermal you're trying to do pretty much anywhere and you're trying to make it happen? But the mature is this something you can do it in that location because of the geology. So it's more.
Yeah, it's not just the geology, well, it is the geology. It's fluid is already flowing through pre-existing permeability versus you have to engineer your permeability. And so people talk about, make these estimates of like heat capacity, like we have this amazing global heat capacity, we could engineer, we could transition, but like what's your potential for recovery of that heat capacity? And so you're looking, Alex has talked about recovery with CO2, people are doing like trialing recovery with liquid water, like you have to somehow take a working fluid, throw it through and recover that heat and either transport it to surface or utilize it in place in the subsurface.
Until we get nanotechnology to do it in a different way, yes, that's how we need to do it.
Yeah. So these are leading edge. And so like I haven't looked into it in the last couple of years, but last time I looked, there's a couple of kilowatts globally. Like whereas I've been involved in projects in Sumatra in the last 4 years that has turned on sort of 280 megawatt natural systems, where the fluid is naturally advecting through the karst from like an upflow zone that's connected to wider recharge. So it's like a deep convection system, and it advects through the karst up through what we call a reservoir area, and a reservoir area is just a connected network of fractured rock, and then it flows out. And it's not necessarily fractured basement in the oil and gas terms. It's often a lot of locations are mixed stacks of volcanic rocks. There are some basement developments like older metamorphics, but they're rarer and tend to be like smaller resources. And there are places where you're producing out of sedimentary deposits like the Salton Sea, which is a mega system in California. So the first development was Laterallo. The second development was in the late 50s in New Zealand, here in New Zealand. And that was wet steam, Laterallo's dry steam. And so you put wells in the ground, and if you have enough temperature, they self-discharge through the energy of boiling. Or if they don't have enough temperature and you happen to have a hydrostatic head, they'll self-discharge through the natural groundwater head. Or you put line shaft pumps in if you're low enough temperature for the like technology of the pump. You're not going to cook your pump, and then you can pump them.
I think in the UK, Steve, I think enhanced just means it's just like a pseudonym for fracking.
Yeah.
Nobody likes to use the F word. Nobody likes to use the F word in the UK anymore.
But you're not fracking shale. You're fracking magmatic rock.
Anything.
Fracking granite or whatever. Fracking basalt.
But you're basically increasing the pressure to fracking to increase the permeability. Exactly the same as shale gas, but fracking has such a negative connotation now that nobody likes to use that word. So it's enhanced permeability instead.
Yeah,
you wouldn't use the same chemicals that pull out the shale oil or gas. One thing that I would add for Steve is that there was a lot of springs at the very beginning. So the baths, the hot baths, were the way that energy was used at the beginning, which started being turned into electricity. The main reason why EGS is such a big thing is that there's the ring of fire that has high enthalpy regions. There's the hotspots like Iceland and Canarian Islands and so forth. And the rest of the world has all of this other potential that doesn't necessarily have these hydrothermal convective systems. And so there is a very large potential, a very large possibility for heat extraction, be it electrical or direct usage from EGS. And for Irene, there have been more successful EGS projects, especially in Australia.
I'm sorry, are you referring to Habanero in Australia as a success?
Referring to the Cooper Basin.
Oh, the Cooper Basin, right.
Yeah.
I was just checking because
Yeah.
then we need to have a discussion about what you call success.
Well, that's the thing. Like, the Cooper Basin failed.
Yes, that
And
also failed.
The reason why it failed is because it only created 10% of what they promised. So
that's the published reason why it failed.
Oh, okay. Yeah, sure. You might know more about that than what I
There's a whole mess of geochemical problems as well, which aren't fully discussed, that were revealed.
I'd love to hear more about that. But mainly, like, EGS step by step is starting to get to that critical mass that is required for it to finally work.
It would be like in my professional lifetime in geothermal, I see it creeping along, and I feel like the ground surge energy behind it. But I sometimes feel like if you were talking about, like barriers, one of the conceptual barriers for like political buy-in, like is often these, like it was the Australian bubble. There was a huge amounts of investment in EGS in Australia, like so much so that they even hosted the World Geothermal Congress. There was so much interest and so much investment, and they were over-promising based on this heat capacity, but not talking about the fact that we don't have a mature technology. We have a research technology. We're still working out how this works. And like subsequently that bubble's burst, like there is much less interest in geothermal after those failures. And I feel like it's, so much was learned from those projects that it was actually the conceptual framework that was the problem. And the same thing happens in natural advecting geothermal systems, that people rock up and say, it's 150 megawatt resource. And they set themselves up for failure at the start, because actually they could have a very economic, very tidy, very developable 40 megawatt resource or 25 megawatt resource. But if you develop that and you do really well at that, people turn around and said, wow, you didn't get your 150 megawatts, you failed. And I feel like EGS is going through the same thing.
Yeah, Australia in the last decade was a real high up and down, and more down than up. I started in 2012 my PhD working on a planned triplet there that got reduced down to a doublet and then just to one borehole, and then they finished it, I think, with a borehole heat exchanger.
No, yeah.
And, like always when I speak to Klaus Regenauer Lieb, who was with CSIRO and stuff, and he gets frustrated more and more.
Oh, yeah, heartbroken.
And I think that this modularity that I was talking about before could be one option for this, where if you can simply just say,
well, let's see if I can get on the thing right.
You have one borehole and you start producing from that borehole. Can you be economic from that? Then add a second borehole. At which point do you start becoming economic? Because at that point, you can increase the amount of boreholes and the amount of modules of energy conversion to the point where the subsurface can allow it, instead of saying, this is the maximum, we're going for the entire thing all at once.
I absolutely agree that this is an excellent strategy, but often the context of what makes a project economic is not what you install at the project, it's the transmission to the client, to the end user. And so I was involved in a resource exploration and evaluation in northern Chile, up near the border with Bolivia, and an extremely high quality resource, but we walked away because the distance to transmission meant that we needed a huge number of megawatts, and we couldn't get certainty around that number of megawatts to be able to commit to go forward with the exploration. And so most people who are looking at the modularity right now are actually looking at, if you're doing exploration in really remote locations that you don't have energy to site, like a line to site, you do a wellhead generator to reduce your costs of exploration so that you can actually self-generate as you build your project. And that's exceptional. Like it does make a huge difference. But like when you're thinking about economics for projects, unless you have an existing transmission line, switchyard, all the infrastructure, connection to the grid, systems and processes to do that, or you've got a direct heat use client or a direct energy use client right there. So for instance, Lahia mine in Papua New Guinea sucks the geothermal water out of the mine and generates power for the mining operation. So those situations work really well, but it's often the economics is just dictated by the power market, the price you can get for your energy, the buy-in price, any subsidies from the government, and the transmission line. The economics are much less dictated by what you do on site.
Yeah, thanks.
Love modulars though.
I asked in the geothermal Slack if there's any engineers around who can wrap their heads around the 50% more efficient organic Rankine system they've had, their marketing, because I haven't found any actual scientific comparisons that they base that on. I don't know what it is that they're describing. I'm not saying they're wrong. I don't see the science to be able to compare anything, and if I would see it, I might not be the best person to understand it. But the way I do understand it, by changing the pressures that are inside of the system itself, they have been able to reduce parasitic consumption somehow. So by doing that, the lowest temperature that they're capable of producing electricity becomes 70 degrees Celsius if you have enough flow through to work with. So these kind of developments, it seems to me like there's so many people throwing everything they have at this, and there's just this one moment, this critical mass that is required for it to step beyond something, and from that point on, it becomes bigger and bigger and bigger by itself. Or we continue making big mistakes, and at a certain point the public says, we're not going to allow you to play anymore.
I think you're right on the money, Alex, that there's just over 170 developed geothermal reservoirs, high temperature geothermal reservoirs in the world, where high temperatures anything that self flows under discharge. Is there anyone from oil and there's oil and gas people here, right? Do you have any idea how many developed oil and gas reservoirs there are in the world? It's in the thousands, right? You're on mute,
Steve. You're muted.
I would say
yeah, David.
tens of thousands, I would have thought.
Tens of thousands?
Yeah.
Tens of thousands? All right. And my best friend's a forester. She's a forestry modeler, and a report came out from IRENA, the energy agency, a couple of years ago, saying how many people are in direct employment in the geothermal industry globally for high temperature, and it's smaller than the Canadian forestry industry.
Yeah, I can believe that.
And but that's those special sweet spots that are over 240 degrees Celsius, have enough permeability to be able to access in the near subsurface, are advecting, are safe to access, aren't way up a mountainside where your civil makes your project impossible, and you manage to successfully drill it. What you're talking about, Alex, is if we can get lower temperature, do cheaper, shallower wells nearer to clients, because people don't tend to live up the side of volcanoes, where we can shorten transmission lines and do it right in place. Jan, you're smiling. EGS, we could do that, right? Yeah. Put it right near the people. Then actually we've got something that's really different to that mature technology.
Yeah.
One of the other things I was just reading the other day is this: who owns geothermal heat? And in the UK, this is an issue. We don't have any regulation. I think in Holland they have the same rules for geothermal as they do for oil and gas, but in the UK it's kind of, anyone can do it, but who owns it?
In New Zealand, because our tangata whenua, our indigenous peoples, have a long view context on the landscape and a connectedness with the landscape. We say technically that nobody owns the resources, we are custodians of it, but in New Zealand, all of our geothermal resources are developed in co-partnership with the indigenous people who belong to those resources, as kaitiaki, as guardians of those resources. But it differs. And actually, David, I think you've touched on one of the key barriers to geothermal development. I've worked in projects in Chile that have fallen over because of a lack of community buy-in, because they have very complex relationships to water, and in Indonesia also, and so working this out socially and culturally, who owns this, not just who owns it, but who should have a say, is really important.
Yeah, I think so. It's we talk about leadership and regulation, and I come from an oil and gas background, and we have all those regulations and licensing and all that sort of stuff, and you pay a percentage of your barrel to the government as a royalty and that sort of stuff. But the comparison of geothermal to oil and gas, I think, is holding it back a little bit. They need to they come up with some regulations to how it's going to work for the geothermal industry, not trying to kind of say, well, it's a bit like oil and gas, so we'll do it, and we'll license things, and you pay a license fee and whatever. But I think if they want to move it forward, they're going to have to come up with some kind of incentives, because comparing geothermal to oil and gas is just not, the amount of energy is not comparable. So
but I would like to add something about that, because I think that probably it will be actually like a positive point. I'm from Colombia, and we have there, like this social thing about like, okay, companies are coming to our country, extracting our resources and take it away, right? That happened with oil and gas or minerals. And for that, the geothermal, it will be socially more accepted because it's something that you are going to use in your community, right? That is going to stay there. You are not going to take that heat and take it and export it, right? It's going to be used in the community. So probably that twist to help, it will help to the community to accept this type of energy a little more. And, you know, for many countries as Colombia, like, you know, developing our resources, it might be a good narrative.
Yeah, but my view is that if you don't have any kind of regulation, don't have any kind of protection for the investor, then no one's gonna do it.
Too risky.
It's too risky.
So I feel like they're two different but related points, and I absolutely agree with David's point. So it's interesting to hear that UK is sitting under an oil and gas type. In Chile, they were using mineral licensing approaches that sets lease areas in blocks. And then sets the timeline for what you have to do in terms of your exploration process, in terms of when you have to drill and when you have to produce results, or otherwise you have to give up your lease. Like based around like this mature minerals industry, noting that they only had their first development a few years ago in geothermal. And it's actually a barrier because it doesn't acknowledge how that resource development process works. And so David's totally right. You need a local regulatory framework that is suitable for the geothermal development. And with Diana's point, absolutely, like I think that there's high potential for social buy-in. But I know in New Zealand and a number of times we've had Japanese delegations here, because in New Zealand and in Japan, people have a very special relationship to the surface manifestations. And historically, our mature technology in the early days developed resources without reinjection. And so it destroyed all of the surface manifestations. And so it's a barrier because social and communities, they have these long-term relationships to bathing, like what Alex mentioned. This is the first usage. And now we have technology where we can develop resources without dropping the pressure, so the natural surface discharges are maintained. But because historically that wasn't the case, this is now a barrier to developing a lot of resources worldwide. It's getting people to understand, hey, look, you know, like we can do this development for your community and also preserve your special features, the places where you bathe, the places where your tourism goes to. So
I think there's a separate part to that as well. I mean, you're describing places that already have these hot places, and I feel that the connection to geothermal is part of the community itself, which might be like something you can hold on to, something you can work with, something you can, like as you say, it's absolutely vital. You don't destroy anything. Like, as people were working in the past, they did what they could, and now we know much better. I've heard of some projects, I think it was in Poland, who didn't have something like this. They just had a borehole heat exchanger that was very deep, very long, created some direct heat usage that clearly benefited the community from cascade heat usage and these kind of things. But additionally, they created a fountain, and they very clearly, like the politicians went to the people and showed that this is something that geothermal created for them. So whenever they went out on the street, they could see that geothermal was doing something. And one of the benefits of geothermal is that you don't need entire parks of wind turbines or an entire field of solar, but it's also a downside. You don't see it. So I think people who already have a connection with the hot water and what it can do for you might buy in faster than people who've never experienced anything with it. But it's very delicate, as you described.
Yeah, I think in terms of regulation, there's kind of two things. First of all, regulation is there to protect the geothermal resource, so it doesn't become depleted. It becomes sustainable in the long term. And secondly, if you're the licensee, it protects you from other people coming in and working in your license. But in the UK, we don't. What I was saying was we don't have that regulation at the moment. We don't have any regulation on geothermal energy in the UK at the moment. So
do you also not have like regulations on the impact that you're allowed to have on the surrounding system?
Yeah, I think that's like environmental legislation, and that's the only thing that really covers geothermal at the moment.
I'm also talking about like ground source heat pumps. I mean, there's certain places where you don't want to change the temperature. For example, if you have the catchment of your groundwater.
Yeah,
like
but we don't have regulation for that.
If I have a ground source heat pumps or several, and you want to install one right next to mine, then they're going to interact with each other.
Exactly, yeah.
And so there are laws in multiple countries that say like you're not allowed to be this close.
Not in the UK.
All right.
Wow. Wow, it's like the Wild West.
Yeah.
What about elsewhere in the world? Or is anybody else connected to their industries to know that they have frameworks? Diana, what's the situation in Colombia right now? Do you have a geothermal exploration framework?
It's very early actually. They just last year started talking about geothermal as its own. Before, so far, there are like things like yes, environmental. They take borrowing things from the oil and gas and the mineral, but there is not like a specific one. But there is an initiative now from the government to really develop that along with other green energies. So yeah, it looks alike around there, but it's still early. Yeah, still in the early stage of legislation.
Like in my view, I think government investment in terms of investing time and energy into developing appropriate regulation, and also de-risking greenfield exploration. In New Zealand and the 50s and the 60s, our government owned drill rigs, and they went and drilled wells in every potential high temperature resource. And so the wildcat exploration was de-risked. And so companies could come in and then have a fluid chemistry sample, which tells you through mineral memory, deep reservoir temperatures, and some information about the subsurface before they commit, like go and find investment for development. So that was investing in regulation, investing in de-risking, but then also investing in generating the kind of power stability and framework, stability in your buy-in prices or some kind of subsidy to make sure that, like this baseload generation can be developed, are the key barriers that I can see for all kinds of geothermal development. Because we get the payback of utility over utility timeframes, 30-year investment, but we have to behave like a resource company and hold resource teams who go out and, like have failed exploration projects. Every developed resource I know has dry holes in it. Like has had moments where projects have gone on hold because, like you're not sure where it's going to go. And it's a really hard mix, it's not an engineering thing. Yeah. We're trying to mix them together.
That's exactly how I answered Alex's question. It's in oil and gas, it's 3D seismic and wells are the standard ways of characterizing the subsurface. you have electromagnetic methods and gravity methods and other non-seismic geophysics, but they're kind of, nice to have. They're not crucial to characterizing subsurface. But if you've got a government program of data acquisition to help you gain confidence in what the subsurface actually looks like, then that's the way. That's the way forward.
Absolutely. That's and I didn't realize they did. I've actually never worked in oil and gas, but that's the other thing our government did early on, is they went out and they did a Schlumberger resistivity sounding for the entire province that identified the general extent of all shallow resources in our main geothermal province here in New Zealand. And when I work in other countries where people are trying to get geothermal going and they don't have that investment, they look at New Zealand. How is it that you have this thriving geothermal industry where 18% of your energy in terms of electricity comes from geothermal generation, and you have the largest direct use heat industrial areas as well for milk manufacture and timber drying? It's because of that early phase of de-risking, I think.
Very cool. So we are getting to the end of our 1.5 hours, and I'm really sorry that I'm stopping the discussion as it is, because I'm having an awesome time. Thank you all for coming. As this is something that's available on YouTube and other people can see, firstly, I would like to ask you, if you want, to share this with other people so that they can contribute to and maybe learn from what we've been discussing today. One thing that I still wanted to show is that if you go on Slido, which is open right now, the questions, except for questions 1 through 4, which are ranking lists, the other questions have a poll which shows what the question is. And if you write your answer in here, then we will only get the answer. But if you write your answer in here, then other people will be able to upvote your answer so that we also get some kind of like ranking of which ideas are better and not. And so with that, I think that I'm not completely sure if we're going to help geothermal energy proliferate with what we've been discussing so far, but I am extremely optimistic about the people that have now come together, the discussion that we've had. And I'm really happy to be working with something so interesting. So wherever you are, have a great day, night, week, life. And thank you for coming.
Yeah. Thanks very much. Thanks, everybody.
Yeah.
Thanks so
I'll add
much
one more
for putting
thing.
together.
We can continue this discussion in Slack, and I think the sheer number of questions, I think Alex is going to, try and find ways to keep taking this forward over the next couple of weeks. So like the polls are active until the 1st of April.
Oh, okay.
Maybe if we can figure out how to get this in front of more people, are happy to keep figuring out how to do that, as in posting on this, Swung channel on LinkedIn or whatever to reach the right audience.
Geothermal Congress community to show interest. Let's see how that works. And otherwise, the answers of this will most likely be a part of either the Transform 2021 or the Geothermal Hackathon, which is the 13th or 14th of May.
Cool.
So, to be continued.
Yes.
Okay.
Thanks again, Alex.
Thanks a lot.
Everything together.
Thank you.
Thank you.
It was
Bye.